In this tutorial, I'm going to show one of the advanced features of Mason, which is its ability to take a circuit design such as this. This is a model for a coplanar waveguide T-Junction, and convert that into a new dynamic file, a new primitive file that can be then used for further simulations. So we can take this file and this is actually the output of this is what generated this model that we use for the coplanar waveguide. So I'm going to pull up the plot. So we have two 50 ohm ports that are in parallel, fed by another 50 ohm port. So what we would expect is at low frequencies, this would be 25 ohms, and then as you go up in frequency, parasitics are going to cause it to be something else. So the way that we have this defined, we have this variable block, and this variable block has just variables that will eventually become arguments in this coplanar waveguide T model. And you can't really have any variables other than that. And as a general rule of thumb, I like to put double underscores in front of these variables, and it helps the internals within Mason not get confused. So next, we have these calculations. These calculations are the sort of meat of how you go from these variables to the circuit parameters that are used in this model. So for example, we have the physical dimensions from the variables feeding into some ultimately width and length parameters for this flat wire inductor. This is some inductance that corresponds to a line with a certain width, length, thickness, and conductivity. Now, in order for the primitive file to have variables mapped correctly, all the variables need to be mapped, all the calculation variables need to be mapped to a reference designator, and then 3 underscores, and then the variable name that this is actually getting mapped to. So technically, because the double underscore width corresponds to the variable name, what you really have is you have the reference designator, a single underscore, and then the variable name that's prefaced with 2 underscores. And that's equal to something that's been calculated. So here, this WA corresponds to just a variable. This L2 length, that corresponds to something that we calculated above. So we go through all these calculations, and for example, we have this SE2 3 underscore C equals CBA, some capacitance that is calculated there. So we have that double underscore C is equal to the SE2C triple underscore C that's calculated. So it's a little convoluted, but if you follow through all of these requirements, and then we run Mason, so we can see Mason running. It's done. So it's rerun the simulation, and it's also created 2 files because we have this flag set to make primitive. And there's actually 2 files that it creates. One of them is this XML primitive file. You need to add into here these descriptions, what the defaults are. Now, the default that it's guessing for these units is really meters. It's Mason uses an MKS internal unit structure, unless you define something, which we have here, to be 20 mils. So it's guessing that it's starting out at mils, but in reality, all of these are going to be meters. So what you want to do is you want to define, for future reference, of the input, define the width of one of the outputs, and so on. You probably want to add some synthesis parameters, but it does all the calculations, the S parameter math, so that you can actually get the 3-port model and feed that back into a new Mason model. I would also recommend you put in like a history tag to tell people how this was generated. And that would be generated with some model from some paper using Mason's auto something like that, just so that there's a paper trail. And alias and giving the a short alias name is probably useful. So that's one of the files that's output. The other one is it outputs a Matlab file. If your calculations, there's a subset of the math parser equations that's compatible between Matlab and the math parser. And the big one is you want to make sure that if you use the power, I think you want to use power of like AB, as opposed to using AB. And that's actually less important for the MATLAB part of it. And the other part is if you have some sort of integer value like 1, instead of using 1, you want to use 1.0. Because if you go with that extra step, you can actually copy and paste this into C code, and with minor tweaking, put this into your own C functions. This is actually, in part, how the built-in models are done in Mason. And then the final thing is, it gives you the default S11 as a return value. But more than likely, what you want to do is you want to add a couple more S parameter outputs, and maybe even some of the synthesis parameters you want to use as function returns. But it just sort of guesses, some name and some return values that you want to use. And as always, frequency is sort of a free parameter that you sort of assume that you need, and doesn't explicitly have to be put into this model. It's important to note that all of the components here are primitive files. They're all dynamic files. There are no touchstone files in this. You cannot use a touchstone file and feed it into the model. All the devices in here have to be algebraically defined. There's also the assumption that all the port impedances are 50 ohms.